Our next speaker is Shion Yoshimura from Kyoto University. And today he's going to talk about the enhancement of spin wave non-reciprocity and group velocity in a low wave number regime. So thank you, Yoshimura, and please go ahead.
Thank you for your introduction. I'm Shion Yoshimura of Kyoto University. Today, I'd like to talk about enhancement of spin wave non-reciprocity and group velocity in the low wave number regime. Spin waves are the elementary excitations of magnetic materials. One of the representative properties of spin waves is non-reciprocity. This means that counter-propagating spin waves have different frequencies or amplitude, and enables fabrications of building blocks such as magnetic isolators and circulators, which are indispensable for spin wave-based computing. While several spin wave systems have been proposed to induce non-reciprocity, we focused on a ferromagnetic bilayer. This is composed of two ferromagnets with different saturation magnetizations, and despite its simple structure, it exhibits considerably large non-reciprocity. Thus, it has been extensively studied in recent years, and the spin wave dynamics in the bilayer has been theoretically and experimentally explored. The figure on the left represents dispersion relations of spin waves in a ferromagnetic single layer. The multiple modes are formed by dipole coupling between Damon-Eschbacher mode, DE mode, and perpendicular standing spin wave modes, PSSW modes. In the bilayer, the coupling strength is different depending on the sign of the wave number, so the dispersion relations become asymmetric, and frequency non-reciprocity is induced. Previous studies have predominantly focused on the spin wave dynamics in the high wave number regime. This is because PSSW modes in the bilayer display significant non-reciprocity at high wave numbers, and these modes are accessible through optical methods such as Boolean light scattering. However, the group velocity of the PSSW modes tends to be low. Because the group velocity corresponds to the slope of the dispersion relation, as shown in this formula, the velocity becomes lower at high wave number. It becomes a bottleneck for high-speed information processing and leads to the increase in the transmission loss. In addition, it is difficult to excite or detect the PSSW modes with microwave antennas. Because the antennas generate a nearly uniform magnetic field along the thickness direction of the ferromagnetic layer, whereas the magnetization dynamics of the PSSW modes are non-uniform across the film. When realizing spin wave devices, a microwave antenna is one of the possible candidates for converting electrical signals into spin waves, or vice versa. Therefore, we aim to achieve strong non-reciprocity with Damon-Eschbacher mode, which possesses high group velocity at low wave numbers and is accessible by using the microwave antennas. Next, we'll explain how to achieve the objective. These figures represent the dispersion relations when the total film thickness of the bilayer is 50 nanometers and 100 nanometers respectively. As said before, these modes are formed by the coupling between multiple modes, and when the bilayer thickness is changed from 50 nanometers to 100 nanometers, frequencies of the PSSW modes are reduced, and higher order modes couple with the DE mode. To explain the mechanism, we expand the spin wave modes by using an orthogonal basis, as shown in the figure. Here, n corresponds to the number of nodes along the thickness direction. For example, the n equal 1 component has one node, and the magnetization in the upper half of the film is in the opposite phase to that in the lower half. The DE mode is dominated by n equal 0 component, and PSSW modes are dominated by n equal 1, 2, 3, and so on, respectively. Also, exchange magnetic field is proportional to the Laplacian of the magnetization. Thus, stretching the PSSW modes leads to a decrease in the exchange field and decline the frequencies. And higher order PSSW mode coupled with the DE mode at lower wave number. Therefore, by increasing the bilayer thickness and using higher modes, as shown here, frequency non-reciprocity is induced at lower wave numbers and higher group velocity. We demonstrated this theory experimentally, and the experimental method is shown here. The figure on the left shows the device structure. Permalloy, quartz, and MgO were prepared by using electron beam deposition, and SiO2 insulating layer was fabricated by RF magnetron sputtering. After that, coplanar waveguides were equipped to excite or detect spin waves. In this study, two types of bilayers were fabricated, with a total film thickness of 50 nanometers and 100 nanometers. In addition, 6 types of coplanar waveguides were designed to excite spin waves with different wave number distributions. This is a measurement setup. S parameters S21 and S12 were measured by using a vector network analyzer, and an external magnetic field was applied to the sample. The measurement conditions are described to the right. This is one example of the measurement data. The right half of the graph corresponds to S21, or positive wave number, and the left half corresponds to S12, or negative wave number. Since the raw data contains noise caused by electromagnetic waves, the S parameters were subtracted by that as Tesla. After the noise removal, spin wave signals were clearly observed. The multiplicity of the signals arises from two factors: the wave numbers determined by the coplanar waveguide, and the dispersion relations of several modes. Therefore, it is necessary to identify the wave numbers and the modes of individual signals through fitting. The fitting function was derived from the Landau-Lifshitz equation, which describes the dynamics of magnetization in the presence of an effective magnetic field. And as the effective field, we consider three factors: exchange magnetic field, magnetic dipole field, and surface magnetic anisotropy field. The effect of surface anisotropy field is not significant in the ferromagnetic bilayer, but it was considered as a correction term. Substituting the effective field to the Landau-Lifshitz equation and calculating it, a fitting function was obtained. Here, we assumed that the exchange stiffness parameter A divided by saturation magnetization ms was equal in each layer, and denoted its values as chi. We analyzed the measurement data by using the fitting function. Here is an example of the fitting result of these parameters obtained from the right figure. Also, these are the results gained from other experiments. By comparing them, it was confirmed that the fitting results of these parameters are in good agreement with other results. We discussed the fitting results of the wave number. The wave number distribution of the coplanar waveguides is estimated from Fourier transform of the current density, and the figure on the left shows the calculated wave number distribution. Several prominent peaks are observed, and one of them corresponds to the fitting result. Together with the slide on the previous page, this confirms that the fitting method is reasonable. From here, we'll discuss the fitting result of the dispersion relations. The curves in the figures are calculated from the theoretical formula. The parameters used in the theoretical curves are the average values obtained from the fitting results. Also, the dots and error bars are the result of the fitting. The experimental result is found to be in good agreement with the theory. And we'll compare the results of mode 2 when the total film thickness is 50 nanometers with mode 3 when the thickness is 100 nanometers. The figure represents the frequency differences as a function of the wave number. The figure indicates that minus 1 GHz of frequency difference is obtained at lower wave number when the thickness is changed from 50 nanometers to 100 nanometers. In addition, calculation of slope of the dispersion relations reveals that the group velocity becomes larger. Therefore, by increasing the bilayer thickness, we realize non-reciprocity at lower wave number and higher group velocity. This is a key finding of our research. In conclusion, we successfully modulated the coupling between the Demon Eshibaha mode and perpendicular standing spin wave modes by increasing the thickness of the bilayer, and realized large non-reciprocity at low wave numbers with the DE mode, which leads to the higher group velocity and enables the generation of spin waves with the microwave antennas. These findings will establish a significant design principle for the development of high-speed and low-loss spin wave devices. That's all. Thank you for your attention.
Thank you very much, Yoshimura, for your very nice talk. So we have a question for you in the chat. Olivia Zanani asked, do you know if your experimental magnetic thin film are monocrystalline or polycrystalline?
It's maybe polycrystalline. Because I used electron beam deposition.
Okay. Okay, we have a new question from Jiacheng Liu. How do you receive PSSW modes in bilayer system considering the interface quality?
Well, sorry, wait. I could not understand the question.
So maybe Jiacheng, do you want to ask the question directly?
Okay, thank you for the chair. I'm curious about the PSW, how to achieve this kind of the mode in the bilayer, this kind of the heterostructure, not in the one thickness, you know that. I mean, for the normally the PSW can be excited in the maybe one kind of the materials with the thicker thickness, right? But here you excited pomeroy and cobalt, this bilayer system, to achieve the PSW. So that means the interface quality should be very high to excite this kind of the PSW. Is that true?
Sorry.
I mean, as the PSW should be required by the boundary of the system. So for the
Yes.
normally you want to excite the PSW, in the normal case, you will excite in the one kind of the materials with the thicker thickness. But here you excite this kind of the PSSW in the bilayer system. So that means the interface quality in your bilayer system should be very wide. So I'm curious about this one.
At least in this study, the PSSW modes are not excited because
Not excited.
I use coplanar waveguides, and these are the Demon Eshibaha mode.
Okay. Okay, thank you.
Thank you.
Okay, thank you again, Yoshimura, for your very nice talk.